Our next speaker this afternoon is Mahmud Hossain, Research Associate of Institute of Textile Machinery and High Performance Material Technology at TU Dresden. Mr. Hossain will share with us his insights on developing new generation turbo ring spinning machine up to the angular spindle speed of 50,000 revolutions per minute.
Thank you very much for the introduction. So I'm Mahmud Hossain from the Technical University of Dresden. So I would like to present about the new generation turbo ring spinning machine up to the angular spindle speed of 50,000 RPM. Using a new twisting system. This is the superconducting magnetic bearing twisting system. And so I would like to introduce at first my university shortly, and then I will go to my presentation. So the Technical University of Dresden is founded in 1828. And since 2012, we are the University of the Excellence. There are 5 schools, comprises of 18 faculties. So the mechanical faculty is one of them. And under the mechanical faculty, there are 14 institutes. So we are one of the institutes of the mechanical faculty. So you see that the students, total students is like 33,500. So it's a big university. They are studying in several studying program up to 122 studying program. There are 2 chairs in the Institute of Textile Machinery and High Performance Material Technology. One is the textile technology, and the another is ready-made garments technology or ready-made technology. So the competence of our institute, ITM, is we teach, research, and work along with entire value-added chain for high-performance textile, from the molecular up to the final products. And thus, we have to combine with the development and the simulations and also some product development, also the machine development. So I will focus today on the machine development, and this is our staff. So we have a scientific staff up to 81, and the technical staffs and the student assistant up to 160. They are helping us to make a successful research. As I'm saying, that we are in a group, or I'm in the group in the spinning sector, so yarn production. So the name of my research group is multi-material yarn structure for high-tech applications. So in our group, the research group, the focus is the development, modeling, simulation of the spinning machine, and as well as of the spinning process. Technology development for the high performance fiber. It can be carbon or glass or basalt fiber, and also with the metal staple fiber yarns to make some research. We are also trying to integrate some sensor yarn also, and the actuator yarns for the structural, for the composite application actually. And we are also we have also the research program for the hybrid yarn, thermosetting hybrid yarn. So this is some production of on the right side the picture. So we have some production of carbon fiber, recycled carbon fiber. We are also concentrating, and also metal fiber. These 2, one, and the glass fiber also. So today I will concentrate about the machine development, as I told you. So I'm backing to my original presentation. So the presentation is a part of a research program funded by the German Research Foundation, and it's the fundamental research project. Probably I will describe more about the turbo ring spinning tester and some textile technological investigation. It means the proper characterization of yarn properties. So as you all know, the ring spinning machine is one of the dominant machine. There's a market share above 80%, and because of the best yarn quality and the flexibility of yarn. At the same time, there are some limitation of the ring spinning machine in respect of the productivity. When you compare with the modern spinning machine like rotor spinning machine or air jet, the productivity is much higher, like 20 to 30% higher. The reason is one of the main limitation of the ring spinning machine is the frictional force in the twisting systems. It means the frictional force between traveler and ring, which generates heat. So I have also measured the temperature with the infrared camera. It's like at the angular spindle speed of only 20,000, the temperatures rises at the traveler like 200 degrees Celsius. And it is up to like also increase up to 450 degrees Celsius. So probably with the cotton fiber, it is okay, but with the polyester, like synthetic fiber, it will melt the fiber and deteriorates definitely the yarn quality. That's why at this moment in the industry, it is only possible to spin at the higher speed only with the very good cotton fiber, not with the polyester fiber at that range. So at this moment, the state of the technology, as I've said, you see also in the ITMA, there are many travelers company and the ring company. So they are using very high performance coating system and very different type of some material to reduce the friction. Or on the other hand, they increase the duration of the traveler and the ring. Anyway, the productivity could be increased only like 10%. It's not directly related. You have still the friction. There is also so there are also some other technology like the magnetic bearing system. So this system. So on the left side, this system has been developed in the US in 2007 with some electromagnetic system. So the idea is to completely eliminate this frictional problem. So we are also concerned. We are making some research like last 5 years, and in the framework of the German Research Foundation. And in this research, we have also implemented the magnetic bearing system, but it is a passive magnetic bearing system using the superconducting technology. So this is another type of magnetic bearing system where the system is stable in comparison to the electromagnetic system. You need very complex sensor, and it is also expensive. So I'm just describing shortly about the principle. We need only a permanent magnet and superconducting material. So when the superconducting material is cooled down, then the magnetic flux line of the coming from the permanent magnet will fixed on the superconducting material, and then it is free to move. The permanent magnet will be free to move. It's like the property is like a spring systems. So when the permanent magnet is rotating, definitely there should be some higher centrifugal force, but it will automatically come to the original position to remain at its minimum energy range. So you don't need any sensor like a active magnetic bearing system. I mean the electromagnetic bearing system. So about the objective, I have already described. So it's about the mathematical modeling because it is really important. It is a very new system. We are trying to replacing the current ring traveler system with the friction-free system. So how it works, and very important is how should be the yarn quality and the yarn tensions with these new systems, especially at the higher spindle speed, and also the measuring the yarn tension. So this is the turbo ring spinning machine. We have developed the machine together with the Italian company Sarmates, and this machine can run up to the spindle speed of 50,000 RPM. I mean the spindle speed. The driving and the controlling system has been already modified. And this part is this is the cryogenic system. which is needed to activate this superconducting magnetic bearing system. So you have, this system is the same one. We have integrated in one position of the spindle speed, in spindle position. So this is the cryogenic system. Inside this box, there is a superconducting magnetic bearing system, and this is the permanent magnet. So this permanent magnet will act and impart twist in the yarn, similar to the traveler in the conventional ring spinning process. And definitely the advantage is you don't have any contact between this cryogenic system and the traveler. It will levitate on the in the air. Due to the security, we have some other special features, like I can after 25,000 the security glass should be closed, and it's not a normal security glass. So for the security of the operator. And as you know, in comparison to the traveler, it is a milligram range. So the magnet is heavier. It's like a gram range. When I say like 150 grams, so the moment of inertia is higher here. So that's why I have to also program the setting of the acceleration ramp of the spindle, especially at the beginning. So as I have told you that the machine is there and we have also developed it, but at the same time it is important to predict the yarn tension. So this is the, according to my opinion, is the second limitation. So due to the higher centrifugal force in the balloon zone, the yarn tension will increase as well. So there are some numerical modeling. This is based on the existing systems, and there are different in the yarn path from the delivery roller up to the cups. There are different region is divided or segmented. It means when I say the region 1, it is between drafting system and yarn guide. Region 2 is in the balloon zone. It means from yarn guide and up to the new system. It means the superconducting magnetic bearing twisting system, shortly SMB system. And the highest tension will occur definitely in the winding zone. It means the region 4 between the yarn guide at the permanent magnet and or the SMB system and the cups. And with this program, we can, with this developed numerical method, we can predict the yarn tension. On the right side, this is the during the theoretical modeling, we have to do also the sensitivity analysis, because this is a very complex and dynamic process, and it depends on also the initial value of the during the numerical process. At the end, it is important, and we have done it with the MATLAB. At the end, it is important, we need two main information. It is yarn tension, what should be the yarn tension, and the region 1 to region 4, I have already said. The region 1 is the spinning zone, and the region 4 is the winding zone where the highest tension is occurred. So you see, when I also increase up the speed up to 50,000 RPM, the highest tension will be 350 around 350 centinewton. And definitely I have also done some simulation varying the ring rail and the different yarn count, and as well as with different mass of the permanent magnet. This is a predictive model. It's a calculated by estimated model, because estimated balloon form at the angular spindle is 50,000. So I will show in the next slide that the highest diameter could be like 62 or 65 millimeter. So it is also important for the machine construction, especially for the spindle gauge. So after mathematical modeling, it is also important to validate the model, and that's why I have just measured the yarn tension with a existing yarn tensile strength sensor. But I have used here only one roller, because when I used 3 rollers, the twist cannot be propagated further. So this measurement is I have done in the region 1 with the sensor between delivery roller and yarn guide to measure the yarn tension. So you see also the result. I have measured the yarn tension up to 35,000 RPM. It means at the same time that the machine can run up to 35,000 RPM. Yes, with this new superconducting, friction-free superconducting magnetic bearing system. Definitely, still there is a friction between yarn and the yarn element, but the main limitation, I mean, like similar to the ring and traveler, between ring and traveler, this friction is completely eliminated. So as I have told you that the highest tension even at the 35,000 RPM is near about like 140 centinewton in the spinning zone, I mean, between delivery roller and yarn guide. So I have also measured the yarn tension at different yarn count from 15 to 40 takes. So from this result, I have not found any I mean, the yarn tension above 150 centinewton takes. Centinewton takes, right? The balloon form has also been recorded up to 30,000 RPM with different spindle speed, and with the image analysis program, it is very easy to determine the maximum balloon using one balloon control system. So the highest tension at the angular spindles of 30,000, it is 62 maximum balloon diameter. As I have told you that the highest tension will be occurred in the winding zone. It is between the twisting system and the copse. So that's why it was also important to measure the yarn tension at this area, I mean in region 4. Definitely it is not easy to measure the yarn tension at that area, but when I know the friction between the yarn and the yarn guide, so I can estimate the yarn tension at the region 4 in the winding zone, considering the coefficient of friction between yarn and the yarn guide. So at this, for this purpose, I have used the constant tension transport equipment, where I can measure the coefficient of friction with different takeoff speed, which should be corresponding to the delivery speed of the ring spinning machine, and the delivery speed machine is definitely also corresponding to the different spindle speed. It is clear. So when I estimate, considering the coefficient of friction between yarn and the yarn guide, and also the measured yarn count in the region 1, then the highest tension at the spindle speed of 30,000 should be like 175 centinewton. So the important thing is also that I can speed up that system, but the yarn quality should be also good. That's why I have also made some textile technological investigation. It means the standard yarn strength measurement. So you see the SMB yarn is the superconducting magnetic bearing yarn, and the ring yarn is using the existing ring traveler twisting system. With the existing ring traveler system, I have spun yarn up to 20,000 RPM, and the yarn strength has been degraded like 6.7%. So at higher spindle speed, the yarn quality degrades. This is the tendency with the higher spindle speed. And now I have tried with the SMB superconducting magnetic bearing twisting system. I could measure up to 30,000 RPM. I mean, I could spin the yarn full copse up to 30,000 RPM, and the value is also remains same without any deterioration of the yarn strength. So this is the important information at the higher spindle speed. And you see when I compare with the Ooster value, it is also very good. Definitely, I have also used a very good input material for this purpose. And in this case, I have used 100% cotton material. So this is the first two pictures of the microscopic investigation. So the first one is the yarn tension, the microscopic yarn view for the ring yarn using conventional twisting system, and the other one is using SMB yarn. And the last one, so I have also spun yarn up at 30,000 RPM. So you see the yarn quality is not deteriorated as expected, because there are no friction, and it helps also for the cotton fiber. You see the further results with the yarn evenness. At the same time, I have measured up to 20,000 with the both with SMB systems and the ring traveler system. So the yarn quality, yarn evenness is comparable. At the angular spindles of 30,000, the evenness of the yarn increased a little bit, but it is also up to now in Uster 25% maximum. So as I have told that it is, I have spun yarn up to 35,000 and make most of the textile technological investigation up to 30,000. So it is also important to know whether it is a possibility to increase the speed up to 50,000. So this theory can be described with a simple a normal distribution. So on the right side, this is a measurement of the yarn strength. It means the measured yarn strength of the spun yarn for the 100% cotton, and the other one is the process yarn tension. It means in the machine. So with this, when I compare these two curves of the normal distribution, these two curves must not be overlapped. Otherwise, we have the yarn breakage. So on the right side, when I have also measured the yarn the yarn strength. So the yarn strength is like from 350 centinewton and up to 70 centinewton. So the lowest, the weakest point I have to consider for the process stability. And then the lowest point is also 350, which is much higher in compared to the calculated winding force, even at the angular spindle speed of 50,000. So there is still the potential to increase the spindle speed. And as you know that this is the only place ring traveler system and the twisting system, but there are also some other friction area like between yarn and the balloon control ring, and also at the yarn guide. So I would like to conclude my presentation. So in the conclusion, I would like to describe the theoretical model of the yarn path has been done up to 50,000 RPM. And the machine has already been developed and integrated the turbo ring spinning in the turbo ring spinning tester and the superconducting magnetic bearing system, twisting system. And the measurement has also done with some developed or modified sensor, I should say, with one roller sensor. The balloon form was also recorded. And the yarn strength, as I have told you, reduced for the conventional ring yarn to some extent, but for the SMB yarn retains the yarn quality, even also at the angular spindles of 30,000 RPM. The evenness test has also been investigated. So, and in the last slide, I have shown you that the comparison of the normal distribution between the yarn strength and the process yarn tension, so which also gives us the possibility to increase the speed much higher. So I would like to thank you all, and I would like to thank the German Research Foundation, DFG, for the financial support. And for the superconducting magnetic bearing system, we have a research partner, IFW Dresden. This institute is also from the Dresden, and is a very world-renowned institute in the area of the superconducting magnetic bearing system. For the further question, you can ask me here, and you can contact with me. And also, I would like to welcome you to visit our stall. It's stand D218. It's opposite to this hall. Thank you very much to hear.
Are there any questions to our speaker?
Thank you, Dr. Hossain, for this very impressive work. I presume the distance between the superconductive material and the ring is critical. They are not touching each other,
yes.
Are they?
No.
So I just wonder the distance between them. They need to be...
It depends on the, you want to know the levitation distance, yeah? Mm-hmm. So currently we are working with 1.5 millimeter.
Right.
So when the distance is more, than you have less magnetic force. Mm-hmm, mm-hmm, and mm-hmm. when the distance is very less, then there is a risk of the sliding on the surface, the other surface. So We are now working with 1 millimeter and up to 1.5 millimeter.
Thank you.
But you can also increase the levitation distance up to 4 millimeter.
Okay, and how about your ring diameter you worked here?
Yes. For this research project, we have considered probably inner diameter is important. It's a 50 millimeter.
50 millimeters,
50
right.
millimeter.
Okay.
And the outer diameter is 80 millimeter because the magnetic force also depends on the volume of the magnet.
Okay. I have one little question, but you showed that the tenacity of yarn increase as you increase the spindle speed.
My
How do you explain?
tendency is not to increase the speed the other way, that it
Perhaps
doesn't.
statistically not significant, but I just wanted to
it doesn't
get your
decrease.
opinion.
This is the information because
Right.
you know the yarn quality mostly depends on also the draw frame system. So the spinning system, it is also it's not decreases.
All right.
No negative.
That's the main.
yes.
Yeah, that's the main
Yes.
point.
Yes.
Okay, thank you.
Yeah.
Any other question?
So
So thank you to our speaker.
thank you very much.